So good afternoon, everyone. Let's wait a few more minutes before we start this afternoon session. So in the meantime, are there questions concerning what we've seen this morning? Yeah, I think so. I think there's no problem. So I guess Professor Leonardo Guidoni doesn't have any problem in sharing his slide. So yes, they will be also available. Well, I guess I can start with a very brief recap, okay, of what we've seen today. So we have this NISC algorithm, like VQE for quantum chemistry, QA for optimization, QNN. What can we say about them? We okay, here you can find some papers that explain better here this part of hardware efficient ansatz for VQE. I guess here we have another paper about QAOA. For what concerns quantum machine learning, I suggest this paper here that show, which is like a review. It's a very recent review of all the proposal of quantum circuit that can realize the quantum neural network. Okay, this one is a very interesting paper by IBM. So basically, they show that they proved that, I mean, the mathematics show that a quantum neural network of this kind may have some, maybe more powerful than the classical counterpart, and could be more powerful in generalizing, okay, when you go from one dataset to another. Okay. But okay, this is a pretty good start, a good review of many quantum neural network proposal. Cindy? Okay, okay. Okay. So I think that we can finish this first part about NISC devices. And we're going to see an application of QAUA to the to the maximum independent set problem, and we're going to apply it. We're going to see the implementation in Pulsar, okay, of this QAUA for neutral atoms device, okay. So we're going to formulate the QA as a sequence of pulses and try to solve the maximum independent set problem, which is an hard problem. then we're gonna go to the real topic of this afternoon, which is quantum communication and cryptography. Okay, so what is the maximal independent set problem? So basically, you are given a graph like this, and the task is to color the largest number of nodes as possible, avoiding to color nodes that are collected by an edge. Okay, this problem is a combinatorial optimization problem belonging to the class that we've seen yesterday, NP-hard, and it has many real-world applications, like in modeling and optimizing dataset, massive datasets that can be represented as graphs, or wireless network, or also modeling. So when you try to match molecular structure, you can also come up. You can encounter this kind of problem. So there are many applications. Okay, to give you a better understanding of the problem, okay, let's consider this. So we have to color blue or white the nodes. Okay, it has to be blue or white. So in this case here on the left, so this is not an independent set because we want the nodes of the same color to be not connected. So here there is this problem, okay, that we have these three which have the same color and they're not connected. They are connected. Okay. So if you look at, so this is not an independent set. If you look at this, the problem in the middle, you see that problem that nodes color do not share. So they're not connected by an edge. So this is an independent set, but this is not maximal. The maximal one is the one shown on the right, of course. Okay. Okay. Is it clear? So how many of you are here? So more than 40 people. Okay. Yeah. Okay. So what we want is to formulate the problem as a combinatorial optimization problem. So like in a cubo form. So we attribute a binary variable to each node. So each node so it's associated with a single variable zeta I, which is 1 if node I is colored, so if it belongs to the independent set, and it is 0 otherwise. Okay. So the combinatorial optimization function associated to the maximal independent set problem is the minimum, okay, of this cubo function. Why? Okay, let's consider each term. Okay, this term here is minimum, reaches its minimum when all the zeta i's are 1. Okay, so this term here forces the zeta i's to be 1. Okay, because if they are 0, you get a cost function of 0. But if they are 1, you get -1 every time they are 1. So you get a lower solution. And since you want the minimum, these are better solution. Okay, so when the i's are 1. But then there is this other term where u is much larger than 1. And what you want here is, so what this term tells you is that whenever zeta I and zeta j are both 1, so are both colored, but they share an edge. So this symbol below the summation means I and j form an edge. So there is an edge connecting I and j. Okay. So if they are both 1, so they're both colored, but they share an edge, then you get a positive contribution. Okay. That is added to your cost function. Okay. So the minimum of this function is exactly the maximum independent set. So the set of nodes that are colored which do not share edges. Okay. So it's so you can easily verify that this is correct. Okay. So what we're trying to do now is to take this problem and try to implement QAUA on the Pascal device, and yeah, see how the Pascal device can solve this kind of problems using an approach that is the one of QAUA. Okay. So let's repeat again what is QAUA. In QAUA, what you have is this repetition of circuits, of unitaries. So UC is associated with the problem. So C in our case is the cost function. Okay, is the Hamiltonian, or I mean, is this problem here, the Ising or Kubo problem associated to the problem that you want to solve. So it's this one, while B is this other term here, which is associated with this fixed. So it's something that is not associated with the problem, it's something that is fixed. Okay, and both are modulated by this parameter that we want to vary. Okay, the parameter is gamma and beta. Okay. Yeah, okay, of course. In this case, in our case, for the maximum independent set, C is what we have seen before. So the cubo form of our MIS problem. So what we want to do is the following. So we want to realize to define a set of sequences in pulsar that basically are I mean, a set of sequences that realize these two unitaries, UC and UB. Okay. So how we're gonna do this? So if you consider UC, so the part that encodes the problem, you can already understand that the form of the maximum independent set problem resembles the form of the Hamiltonian of the qubit system that you have in pulsar. Okay, so this is what we have seen today. So basically, this term here is mapped by a pulse with since both are zeta terms. This term here is mapped with an appropriate detuning. This other term here is mapped into the Hamiltonian of pulsar using an appropriate topology. Okay, because zeta zeta j is like having ni and j, because ni and j depend on zeta and zeta j. So basically the same thing. So u depends on the distance between qubits, which means yeah, so reflect the edges in the graph that you want to of which you want to find the maximum independent set. Then there is this B part. B part is mainly this one here. okay? Because you have the, as we have seen before, the sigma x terms that appear here, okay? So let's go on and try to do it. Try to do this on Pulsar. Okay. Yeah, let's go to the Jupyter notebook that you can also find here and on the GitLab, and it is this one. Okay. So this what I will do here is describe more in detail in these papers here, also from people from Pascal. Okay. So the idea, as we said, is to find is to use QAUA on this analog quantum computing device based on neutral atoms. And so QAUA based on this sequence of pulses and try to solve the MIS problem, okay? So what could be the application, okay? MIS, an example is in let's say optimizing Wi-Fi network or cellular network, okay? So for example, like in this case, they have the different cities in France where they placed the antennas, okay? And each antenna has some frequency, okay? So each one is a Wi-Fi antenna, I don't know, or cellular antenna, okay? What they don't want is that antennas that okay, each antenna has some radius, let's say some radius of transmission, okay? So each antenna can transmit within its radius, and so in order to have a proper a cellular network that works fine, we don't want antennas that are close, so antennas where the radius of the transmission radius overlap. We don't want them to transmit on the same frequency, okay? So we want we can see this problem as a maximum independent set problem where we connect antennas, so cities which have an overlap in the transmission radius, okay? And we don't want them to use the same frequency, okay? So that's why we have to color them with different colors, okay? And that's the graph associated with this problem, right? And the solution it will be the maximum independent set, okay? Because if you color red, so let's say the antennas that you color red, you know, have to be need to have a different frequency, transmission frequency with respect to the black wall, the ones that are colored in black, okay? So is it clear so far the problem? I guess so. So write in the chat if you need clarification. So okay, as we've seen before, the cost function looks like this for this MIS problem. And what we want to do again is to map this problem into the Hamiltonian of the Pascal quantum computer, okay? So again, this maps pretty well on get mapped pretty well in the second and third term, okay? While this one will be used for the exploration part, right, of the QAOA. So let's go on. So let's start. So here, what we want to do is to define. First, we define this function that takes in input the position of the qubits and creates a graph where the qubits that are within some distance are connected. Okay. So sorry. Okay. Now this is some. Okay. The question was about the physical. So this term here is, let's say, no, yeah, it's relevant. I mean, they know that the interaction. So this term tells you about the interaction between qubits or atoms that are close. Okay, and they know from experiments, okay, that their interaction decays like the 6th power of the distance. So it's something that they know from. So their physical hardware has this property, okay. And yeah, it's like a physical property of the device, okay. Not sure. So it's gonna be not sure why. So why to the 6th, but it's something that they know from. I mean, that's the way. So when two atoms are close, they know that. I mean, when I mean the interaction strength between these two atoms decays like the 6th power. So it's something that they already know. So it's not coming from this stage. Okay. Yes, I think yes. Yeah, it's the third term. Yeah, it's written here is the repulsive term or the van der Waals interaction. Exactly. Yeah, exactly. Yeah. So yeah, it's gonna be 1 over the distance to the 6th power. Yeah. Okay then.
But is it because we're talking about the S1 electron on the outer layer of the rubidium atom, or would that apply to any sort of atom that could be used in the same phase?
Yeah, I'm not sure if this R to the 6 is associated with the fact that they have rubidium atoms or not. I don't know if it is general. Yeah.
No. I was referring to something else. To the fact that it's described by Valentina as a dispersive term akin to the van der Waals interaction rings a bell, and so I was thinking it must be because we're talking about the S1 layer for the rubidium atom, and maybe if we use a different atom with a different electronic structure, then it would be different. And it doesn't matter. It's not really relevant, I think.
Yeah, I mean, probably yes, but I'm not sure yet. But for sure, it's something related to the van der Waals repulsive interaction. Okay. Okay, then let's go on. Okay, so we build this function here that is post to graph. So okay, what basically are doing is the following. Okay, so here we have zeta I that are binary variables, and here we're going to use qubits. Okay, so each binary variable here is associated to a qubit. Okay, the topology, so the graph is going to be the graph that we have here is going to define the position in the space of the atoms, which means of the qubits. okay? And two qubits are going to be connected whenever they are at a radius that is smaller than the Rydberg radius that we have seen. So, which means that whenever there is an edge, it means that they interact one each other, okay? So they are within the Rydberg radius. Okay, then. So that's why we need this function, okay, to generate. I think I already run this, okay. To create the graph. Okay, let's go on. So here we create an example, so an atomic register with where the atoms are placed in this way. Okay, so the atoms are placed in this way. And then we use the graph to understand which is the maximum independence. Sorry, which is the graph problem associated to this position of the atoms, which is this one. Okay, so basically, yeah, what we're trying to solve is the maximum independent set problem on this graph here. Okay, where each node is a qubit. Okay, a real qubit, and they are placed in space in this way. So in order to perfectly mimic the structure of this graph. Okay. So as you can see here, so okay, this is an easy sample because yeah, this is for an educational purpose. But so you can see, okay, by just simply by looking at this, that the the maximum independent set in this case is going to be when we have when we have the vertices 1, 3, and 4 colored, or the vertices 2, 3, and 4. So there are actually two solutions to this problem. Okay. So since at the end we're going to have we're going to measure everything, and everything is going to be in binary. Okay, when we look at the output of the quantum circuit. So what we're gonna we're gonna see if the answer, I mean, if the optimal answer are these two. So basically, 1, 3, 4 means so since the ordering of the vertices is 0, 1, 2, 3, 4. So when we look for the solution, we have to look for this kind of binary string, okay? Because so we say 1, 3, 4 means in the position 1, in position 3, in position 4, okay? Because this is the order, okay? Or position 2, 3, 4, which means in binary 0, 0, 1, 1, 1, okay? Okay. So I think this is pretty clear. Then, okay, let's start with the creation of the sequence for the MIS problem. Okay, as you know, we start our QA algorithm where everything is in the ground state, so everything is in 0, 0, 0 state. Then we want to apply P layers, P layers here of these two pulses, or these two circuits, let's say, or unitaries, okay, which are associated to these two Hamiltonians. So here the Hamiltonian is C, and here is this sigma x, okay. So yeah, okay, for the B part, as we've seen before, we're gonna have a pulse associated with the Rabi frequency 1 and the tuning 0, okay, because we don't need the zeta term, okay, we just need the sigma x term, as you can see here, okay, just the sigma x. So that's why this is our B part. the second Hamiltonian is going to be the one associated to our problem. So has this term here equal to -1. So the tune is going to be -1. And this term here is gonna it's gonna have the same topology, reflect the same topology of our problem that we want to solve. Okay. Of course, I mean, this term is always present because doesn't have a meaning to select a pulse without amplitude. Okay, so this term is going to be still here, but we also, so because we have the HB part is going to double at some point, no? I mean, it's going to be always present, basically. No, it's gonna. So let's define now the quantum loop. And in the quantum loop, what you do, you first initialize, okay, our sequence. So we give an input the register that we have created here. This is our register, and the device. This is Chadok2. And then we declare our channels, and we're going to use just a global channel, so something that affects all the qubits. Okay. Then we define. So, okay, we have seen that in QA/UA, so in this parameterized circuit, you need to have some parameter. So in this case, in our case, since okay, we can the only parameter that we can associate to our pulses, since Rabi frequency and the tuning is fixed, the only parameter that we can associate is the length. So how long this pulse is going to be. So our parameters that we optimize, so what we have called before gamma and beta, are t and tau, which is the length, so how long in time is the pulse. Okay, so t is the time associated to HC, and tau is the time associated to HB. Okay, and we start with a random situation. Okay, where the t and tau are set at random. Okay, and let's see. So okay, this is the quantum loop. Okay. So, and then we can plot the distribution. Okay, we initialize, okay, the parameters t and tau at basically at random. I think these two are the initial parameters that we give. So it's the first parameter is 2000. So the first t is 2000. The second one is 5000. So pretty random. And what we get, if we look at the solution, is this one. Okay. So by setting the parameters of my QA/UA at random, you see that these two in red are the correct solution that I was expecting. So it's 01011 and 00111 that we know from here that are my solution. So they're not the most probable solutions. Okay, I mean they're not. No, let's say the quantum state that I created choosing the parameters at random do not maximize the probability of getting the correct solution. Okay, actually the probability of the correct solution is pretty low. For example, if I put, I don't know, here 200 and 5000, let's see what happens. Okay, maybe I increase a little bit the probability, but let's see if I use 50 250. So no, it's too short. And 500. Okay, and let's see what happens in the plot. Okay, it went. It was worse. Okay, so it was better before. So I'm gonna try. I don't know, 4,000. I don't know, 4,000. And you can go. Okay, no, it's okay. So no, it was like 5,000 and 2,000. Okay. Okay, this was what you obtained. So you understand that if you do this at random, you may be lucky, so you can get them. So that you can get the probability of having them of having the correct solution on the left part, which means that the most probable could be high. So depending on your choice of the two parameters. So now we have the optimization part. Okay, so what we want is to is not to change the two parameters at random, but we want to optimize them. Oh, sorry. So what we're going to use, so we're going to create the function that returns the cost of a specific graph coloring problem. Okay, so for example, here, okay, it's easy to see here. The cost of coloring all in the same way is 0. So for example, if I get 1, 1, 1, 1, 1, what happens? So it's 45. Okay. So this is the situation where all the vertices are colored, and I definitely increase a lot the cost function. So of course, this is not a good solution. For example, let's try this one. I'm gonna lower the solution. Let's try this one again, 17. But we know that the correct solution is something like 0, 0, 1, 1, 1, okay? Which is solution -3, okay? So what we want, and this is something that evaluates, so given an input, a string, so a possible solution tells you what's the cost associated with this solution, okay? And here we have this function that puts together the quantum part and the classical evaluation, the classical optimization. And yeah, this is just to calculate the cost. Okay. So what we are going to do next is a single repetition. So we are going to do just one. Okay, let me run this because it's going to take some time. So what we're going to do here is a single repetition, which means here I just use one repetition of these two. So if you want to improve the solution, you have to add multiple layers, so multiple P. So here P is a single layer, but for this simple problem, a single layer is just fine, okay? So basically we use this minimizer, this optimizer that whose method is this one is Nelder-Mead method for optimization, classical optimization again. And we start from so the initial point for the minimization is this one, I think. So our first guess of the parameters is going to be this one. I think we can set these two at random as well. And then the optimizer is going to go, it's going to, let's say, it's going to tell us after some epochs, which is the best one to use, okay? And yeah, in this minimize, I put the function that evaluates the loop, okay, with the parameter and gets the cost. Okay, so I'm not sure about how many iterations it does, but you know, you can see here that it is taking some time. So probably like 100 epochs, I don't know. So it's gonna take some time. Okay, that's why I launched it before. So then at the end, what are we going to see here? So we're gonna see a modified version of the. So basically, this tells you the probabilities. So the probability amplitudes of each basis state inside your quantum state. Okay. So after the optimization, what do you expect to see? Oh, sad. Yeah, what do you write me in the chat? Which kind of graph? So we're gonna have something like this, an histogram like this. What do you expect to see after the optimization? You expect the this solution here to be high or to be low? Right in the chat what you think about the solution. This is still going, okay? So it's gonna take some time on my laptop. Are you with me so far, more or less? Can you guess what's gonna be the final histogram? Can you write in the chat? So what do you think about the final histogram after the optimization? So selecting random parameters, you get this quantum state where the solution appears but is not very, very probable. What do you expect at the end after running the QA/UA with one repetition and many iteration, many optimization? Do you expect the red columns to be? Okay, this is still going. Do you have any idea? Please write something in the chat. Also no, or also not clear at all. It's gonna be acceptable. But please write something. Okay. Other people? Let's see if it's finished. No. No, okay, still not. I think the fact that my computer is busy with the Teams is gonna take some time. But okay, yeah, you some of you, yeah, you got it right. Yeah, what we're gonna see is basically the same thing, but where the red columns are gonna be more or less are gonna have the same probability, and they're gonna be the most probable. Okay, with just one repetition of the variation, yeah, of the variational layer here. Okay, so for this easy problem, you just need one repetition. The harder the problem becomes, the more repetition you need to introduce. Okay, and yeah, that's the idea of here. Okay, so it's taking too long, so we're gonna go back at it later. So let me Let me ask you if do you have any. So this is the end of this part. Okay, let me tell you. Something about software. So we use Pulsar and Qiskit, but these are not the only one. I also told you something about Circ that is going to be. I mean, Circ is the Google version of Qiskit, okay, where you can. And in the future, you will be able to program Pulsar at the circuit level using Circ. And it's not the only one. There is PennyLane. This is developed by Xanadu, which is the company that we have introduced at the beginning. They are producing the photonic quantum computer. PennyLane is especially a lot of things for what concerns quantum machine learning. Also, Qiskit has a lot of stuff. TensorFlow, probably some of you that use machine learning know TensorFlow, and they also have TensorFlow Quantum, and probably we're going to see something about these three tomorrow morning when Marco, the other lecturer, is going to introduce quantum machine learning. There is also Amazon Web Service that they also have Amazon Bracket, which is their software. Amazon Web Service, they have like 3 devices available. One is a D-Wave device. Another one is a IonQ, which is a ion trap quantum computer. And they also have a Rigetti computer, which is a superconducting circuit device. Okay, and you can use Amazon Bracket, which is the Amazon version of Qiskit or the Amazon version of Circ to program these other devices. Okay, let me see if this finished. So as you guessed in the chat, the correct solution became the most probable. Okay, in the final state. Okay, this is a reconstruction of the amplitudes of your final state. Okay, after the optimization. Okay, that's what we expect. Okay, and okay, and you understand that what is important in this kind of variational techniques, so hybrid techniques, is not only important to have a quantum computer that is able to perform something that classically, a circuit that is classically, let's say, hard to simulate. So something that involves quantum entanglement to simulate molecules or solve problems, or so something like that. So it's not only important the quantum circuit part, the variational part. It's also important to have a classical optimizer that works well. Okay. Yeah, that was taking too long. Okay, on my laptop. Okay, then. So, are there any questions regarding this part? Otherwise, I'm gonna skip to the real part that we want to see today, this afternoon. Are there questions regarding NISQ devices or NISQ stuff, algorithm, variational algorithm, and so on? If so, write in the chat now, before we start the quantum communication and cryptography part. Can you write something, at least if you are still here, or? Please write something if you're still with us or still following, or tell us if you need some rest after these 4 days. Okay, it's pretty clear, I guess. So give me some feedback. So is it too dense? There are too many things to understand, or is it okay? Or maybe the second day was harder? So which day was the hardest day? Today probably it's a bit okay. No, there is not much mathematics involved, so it's more understanding the general idea, I guess. Or maybe yesterday it was hard as well as the second day. Okay, some of you. Yeah, sure. Yeah, it's yeah, of course. Yeah, need some time to digest the things. Okay. Okay, so let's start with this part. Why? What did he say? Yeah, sure. Depends on the background, yes. Yeah, at the end, I mean, this topic is very interesting because it's also quite interdisciplinary. So you mix physics and mathematics and computer science and neural network and chemistry, and so it's, yeah, you need to have some idea of different areas of science. Okay, but this is something that I like about this topic, right? Okay, yeah, for sure you yeah, well, for sure, yeah, it's gonna be okay. So let's with the okay. So let's go with the second part. This part is going to be about quantum communication in cryptography. Okay. So first we're going to review again. So this way you can see again things that you that we have seen in the past days, and we're gonna I'm gonna recap the things in quantum mechanics that are gonna be useful for also for quantum communication and cryptography. Okay. Yeah. Okay. So brief recap of what you need to know in order to the minimum, the bare minimum that you need to have in mind to understand the next two topics. So again, tensor product. Okay. The thing, okay, the tensor product, I guess you understood that works like this. And something that I want you to have in mind is that you can write the tensor product between states in a compact form in this way. Okay, so maybe you can also write it down because helps you, okay, with what's going on, with what we will help you with the following. So you can, yeah, basically, yeah, write it down. So I'm gonna do it as well. Where is it? Here. So this is equal to writing psi phi, or even avoiding the middle brackets, and okay, put it in on the same state. Okay, it's gonna be useful. Yeah, this is the first thing. Second thing, yeah, okay, we have already seen this one. So the unit of quantum information is the qubit, which is the state here, and you know that a general state of a qubit is this one, alpha 0 plus beta 1, where alpha and beta are complex numbers. And something that I want you to write again is this one. Okay, we can have different bases. Okay, 0, 1 is the canonical basis. So they 0, 1 are the north and the south pole. Okay, here of the Bloch sphere. So the way you represent a quantum state. Okay, it's the surface. A quantum state is a point on this surface. But you can also have. So this is a general okay, thing in linear algebra. Okay, you have some bases, but then there exist other bases that are a linear combination of the canonical bases. Okay, so for example, the plus minus is another basis. Okay, so let me write this also down. So we have canonical basis, which is 0 and 1, and we have another basis which is plus and minus. Okay, so which are yeah, and plus and minus are like the north and the south pole, but when you rotate the Bloch sphere. So here they are on the equator, but if you rotate, they become the 0 and the 1. So you can find other, of course, other bases, but we're going to use basically only these two in the following. Okay, let me make it more clear from the quantum communication point of view. Okay, so for quantum communication, usually you use photons. So photons are the carrier or your quantum the quantum information. Okay. Okay. So these are the physical realization of qubits. Okay, for what concerns photons. Okay, you can encode the state of a qubit in the polarization, for example, horizontal or vertical polarization, in the number of photons. So something is called the Fock state. So if you have no photons, so it's the vacuum, this is your 0. If you have a single photon, it's your 1. Also in something it is called the time of arrival, but okay, I'm going to skip this. And also in squeeze light. So we already talked about this. This is what Xanadu or photonic quantum computer use, for example, that they encode the information in the quadrature. So they could be a squeeze state, amplitude squeeze states, or phase squeeze states, and these are your 0 and 1. Okay, but the simplest to understand probably for everyone is the polarization of light. Okay, you have horizontal or vertical polarization. Okay, I mean it's horizontal or vertical, yeah. Okay, and these are the 0 and 1, and these form your canonical basis. Okay, and you can use quantum effect to have a superposition. So your qubit, so your photon is in some kind of superposition. Okay, and this is the way you implement these kind of things. Okay, especially in quantum communication. Again, the second postulate is the one where it's associated. We say that to a composite system is associated state that is the one shown here in general, and you could have entanglement. So the consequence of this second postulate is entanglement. Okay, and you can have Bell states, right? That are entangled state of 2 qubits. And I want you to also write them down so you can have these possibilities. You have phi plus that is equal to 1 over square root of 2, 0, 0, plus 1, 1. And you have psi plus minus that is equal to 1 over square root of 2, 0, 1 plus minus 0, 1, 0. Okay? If you write them down, you're gonna be easier, probably, okay? I wrote this in this way, in this compact form, so I put plus and minus on in the same. And these are the bell state that we are gonna use a lot in this part. Okay, let's go on. Let me put this here. Okay. Again, this is something that we already know. The evolution is unitary evolution, or unitary evolution of a closed quantum system, so governed by the Schrödinger equation. So an observable, so it's a physical quantity that you measure. It's associated with some Hermitian operator, and each a measurement of this operator, of this observable, returns some values that are the eigenvalues of the operator. The state after measurement change in this way, and you get you obtain a result O of I with some probability that is defined by the modulus of the scalar product square, okay? Modulus square of the scalar product. Okay, no, this is something that we already see. What does it mean in our quantum communication framework? Okay, we have seen already that this encodes our canonical basis, and thanks to them we can define our quantum state. So observable quantities are related to somehow the information, so on how you encode your information, okay? Let's say in the simple case, or where you have the polarization of light, so when the qubit is encoded into the polarization of light, you can measure, for example, linear polarization that will be Z, which is which has like Z as 0 and 1 as eigenvalues, sorry, as eigenvectors. So again, you find this form here of an observable. So Z, so is our observable that we are measuring, okay? So what does it mean? It means to measure the linear polarization. X is like measuring the circular polarization, which doesn't have 0 and 1 as basis, as like eigenvectors, but it has plus and minus like eigenvectors, okay? So when, yeah, this is something that we usually say, no, when we intend, so when we measure things, we can measure, usually people say along Z, which means that we are using the canonical basings as a reference basis, or we are measuring along X, which means that we're using this other basis as the reference basis, okay? And yeah, let's write also this thing here. So what's the action of X and Z on the eigenvalues, on the eigenvectors? Okay, and you have it also here. So you should have written this thing, okay? That will help you understand, okay, the following. Okay, so for example, let me do this example. We start from this initial qubit. Let's say I want to measure along Z direction, which means that I'm measuring in the basis of the canonical basis. So this means that I get, if I measure along Z, I get 0 with probability alpha squared, modulus alpha squared, or I get 1 with probability beta squared, modulus beta squared. But if I measure along X, which means I'm measuring in the basis plus and minus, I get plus with probability alpha plus beta squared over 2, and minus with probability alpha minus beta square over 2. Okay, is it clear so far? Write in the chat or speak. So this was the recap, but the thing that you need to know. Okay, if it's not clear, this part about the measurement, please tell me, because it's going to be, so all the quantum communication, quantum cryptography part is going to be about measuring quantum states. So you need to understand correctly, okay, this part about measurement. So if you need some more so if it is okay, please write yes or plus, or if it's not, please write minus or no. So you can choose your basis. So you can write 0, which means okay, or 1, which means not okay, or you can choose the basis plus, which means okay, or minus, which means not okay. So choose your basis, but okay, the meaning is the same. Some other people, I want some minus. I want some 1 or some minus. Or maybe not. Okay, so you're not completely, so you're confused, Cedric. Okay. So if you are confused, so you're not sure about what to do, okay, no, but then yeah, H applied to 0 is like plus, so it's also okay. H, if it is the Hadamard, okay, H is plus, so it's okay. Yeah, right. Yeah, at the end, yeah, H is basically, in fact, the operator that allow you to change basis. Okay, you go from the 0, 1 basis to the plus minus basis. Okay, but yeah, okay. Okay then, so I guess we can go. Okay, let's start with the quantum communication part. Yeah, exactly. The Hadamard, yeah, it's a change of basis. Yeah, exactly. You go from like allow you to go from one basis to another. So it's like yeah, circular polarization to so linear to circular. Yeah. So okay, let's start with quantum communication. Okay. First of all, classical versus quantum channel. Okay. A classical information channel is a communication channel used to transmit the classical information. Okay. And the unit of classical information we know is the bit. Okay. So the example case is the cables that we have for electric pulses, okay, and they carry classical information. Okay, they carry 0 and 1s. In quantum information, in quantum information channel is a communication channel that can be used to transmit quantum information. So you can transmit qubits, okay, because the unit of quantum information is a qubit, and you can transmit a qubit that is in the 0, 1, so state, but also a superposition, okay. And the coherence must be maintained throughout the channel. So we are considering here ideal channels, okay, where you send a qubit state, and at the output you have a qubit. I mean, if you send a qubit in a state like this, alpha 0 plus beta 1, at the output you have the same state, okay? In general, in reality, channels are noisy, so there is some probability of having some error, okay? Or the fidelity, so which means the scalar product between the initial state and the final state is not 100%, okay? But maybe is not alpha, is alpha minus something, you know, and beta plus something, okay? So you've seen classical communication channels are the electric cables, as you know. What about quantum information channels? So two of the most used quantum channels are, so in free space, you just send a laser beam. So you send photons via laser. So this is happens. So in free space, so you don't have like a physical medium like a cable, okay? And that's what people use also for space communication, okay? So there are quantum communication protocol that have been implemented from Earth to satellite, and they use, of course, this kind of lasers, okay? You send photons via lasers. Or could be a physical device like an optical fiber. The difference basically between the two is that with the laser beams you can go much, you can perform quantum communication protocol at long distance, because basically photons are weakly interacting with the atmosphere, okay? This is so you can also do it for, so you can perform quantum communication at a long scale, like hundreds of kilometers, even thousands of kilometers, I think. And while in optical fibers, you can send photons inside optical fibers, but then you have some so it's like for medium short communication, no? Because after a while you get too much noise and too much error, and the quantum communication after 50, let's say 50 probably kilometers. I think the experimental the record is something like 50 kilometers. After that you get so you lose the initial state, so you get at the end something that is completely different, okay? So okay, these are the medium that can transmit, okay, quantum information. So the quantum channel could be free space or optical fibers, okay? This is just to make you understand more like also how people implement these kind of things. So as you might understand, so actually the realization of a quantum communication protocol is possible today with specialized device, and is not necessary the use, is not necessary. So this protocol do not require actually a quantum computer, okay? You just need some source of, usually source of entangled photons, source of so something that can produce you the qubit, so the entangled photons or photons in superposition, and then you need devices that are able to measure basically and performs also some basic operation on the photon you receive, okay? So that's why, so it's not as hard as constructing a quantum computer, no? It's something that already today you can build. So you can build something like quantum network that use quantum communication. Okay. Then the next step is going to be like the quantum internet, which is when you have a lot of quantum computer, they will be able to talk each other via quantum communication channels. Okay, but it's even more far-fetched. Okay, far it's gonna happen. Okay, especially we need to build some quantum computers. Then we will think about connecting them into quantum internet. Okay, which is a quantum communication plus quantum computers. Okay. Okay, then what's the first thing to have in mind for quantum communication is what we already see in the second day, which is the no-cloning theorem. So since everything is unitary in quantum mechanics, so it's not possible to exactly clone or copy, okay, exactly copy or clone in unknown quantum state. So does not exist this unitary that given an arbitrary state alpha realizes this copy, okay, as shown here, okay. And we also prove this this theorem mathematically, and that goes by contradiction. And at the end, we were able to see that there exists a unitary, but only there exists such unitary, but only acting on states that are classical, so that are orthogonal states, set of states, okay? So, which means that we recover, okay, the classical case where actually cloning is possible, okay, copying is possible. Okay, so let's start with the first protocol. Is it okay so far? Write me something. Let me if I need to focus on something else. Okay, yeah, okay, there's something that I don't remember too much. So there is the whole field of quantum information that basically rephrase all the classical information, so the Shannon entropy in quantum terms. So basically, you don't have Shannon entropy that is for classical physics. In quantum information, you have the von Neumann entropy, if I'm not wrong, which is defined in a similar way. It's always the logarithm of so it's the logarithm of something, but okay, right now I don't remember. So, and you define everything starting from that von Neumann entropy, okay? And 1 second. So, and also the channel capacity. So there are a lot of, so this is the whole theory of quantum information, and the quantum channel has different properties, and that's also involved the capacity of a quantum channel that is not the same as the capacity of a classical channel. Okay, but so there is the formulation of. Give me a second. Quantum. But the quantum information is a course on its own. Okay. So yeah, basically, yeah, it's this one for the von Neumann entropy for so for a quantum capacity of a quantum channel yeah, the quantum capacity, yeah. No, it's not. Okay, however, yeah, maybe later, if I can find some. Okay, there is one book that is from, is this book here from Chuang and Nielsen and Huang about quantum computation, and quantum information. I'm gonna send you the link, okay, the Amazon link. Okay, this is the most famous book about quantum information, quantum computation, and here you have all the, yeah, and that's like the basic. This covers both quantum computation part and quantum information part. There is also something free on the archive. One like famous scientist in quantum information is Mark. Mark Wilde, and he has usually a lot of stuff on also on the archive. I think his book is also on the archive. So yeah, probably something like this. I don't know if it is the book that I'm thinking, but maybe if you look on the archive for this guy, he has a lot of. For sure, he has the book that he writes. He also put it on the archive, so you have it for free. So it's all about the Shannon entropy and so the quantum entropy and so on, and quantum channels. So okay, let's go with the quantum part. So the first protocol that we're going to see in quantum computation, in quantum communication, is quantum teleportation. Have you ever heard about quantum teleportation before? How many of you think it's something like this? So, how many of you hope that is something like this? Okay, by the way, yeah, it's not something very, it's not something so like Star Trek stuff. So it's not something that will allow you to move to reach another point in the universe very fast, but it's something that has to do with quantum states. Okay. So the idea of quantum teleportation is the following. So you have Alice and Bob. They share. So there is a classical communication channel between them. The idea is the following. So Alice is in possession of Dragon Ball. Yeah, of course, right. Okay. So basically, Alice has 1 qubit in her possession, and what she wants to do is she wants to send the quantum state associated to this qubit to Bob, having only a classical communication channel available. So she cannot send the qubit, but using a classical communication channel, she can send the state of the qubit, of her qubit. Okay, so she won't send Bob the physical qubit, what is going to happen? She will teleport the state, so just the state of the qubit to Bob using a classical communication channel, plus another thing that we're going to see. So this is the qubit labeled C that is in the hands of Alice, and Alice, this qubit has some unknown generic state alpha 0 plus beta 1. Okay. Again, remember that Alice cannot make a copy of the state of her qubit and send it to Bob because there is no such thing as cloning. So what they can do is the following. Alice can call a mutual friend of Bob, which lives in the halfway between Alice and Bob, and this guy, which is us, for example, we have a source of that can generate entangled qubits. Okay, and so basically you have an entangled qubit source that you can send to Alice and Bob. Okay, and the state that this source can prepare is the one shown here. So is the state phi plus, which means 0, 0 plus 1, 1. So if you have written here is this state here with the plus, right? Okay. So at this point, what happens? Happens that Alice has two qubits in her possession. One is A, and one is labeled C, and Bob is another qubit. His qubit is B, but A and B are not in a product state, are in entangled state, okay? So A and B are entangled. What does it mean? It means that in this initial case, in this initial situation, the global state of the three qubits possessed by Alice and Bob is the following, okay? We have state C, that is in possession of Alice, whose state is this one. And then we have qubit A and B. A is in possession of Alice, and B is in the heads of Bob. But they are entangled. So even though they are far, so Alice and Bob are far, they share an entangled couple, entangled pair of qubits, okay? So we cannot separate the two states. You cannot write, okay, as we've seen the state of the two qubits separating them, okay, by a tensor product. Okay, oh yeah, sure. So this is the state of qubit C that Alice wants to send to Bob. This is entangled qubit pair, A and B, shared by Alice and Bob, okay? Alice has A, Bob has qubit B. Okay. Is it okay, this initial setting? Is it clear? Please write in the chat. Okay. Okay, then. I'm not going to do that, but it is possible to prove that using the following relations, which are the Bell state that we have written here, right? So with some mathematics, so there is some mathematics involved, but it's not hard. You can rearrange, you can recast this equation here using these formulas, which are the definition of the Bell state. You can rewrite everything in this way. So you can rewrite everything separating. So you use the Bell state to represent state C and state A, which is in possession of Alice, tensor product, a state which is the state of the qubit which is in possession of which Bob owns. Okay. It is going to be a sum of all the Bell states. Okay. So if you want, we can do this, but it's going to be not complicated, but it's going to take some time. Okay. But it is possible to rewrite this formula here, okay, using these equations here. Okay. Then at this point, what happens? So take this for granted. Okay. At this point, so no operation is done. Okay, it's just a mathematical rephrasing of this formula. Okay, it's not something that physically happens. It's just math. Okay, you can see that you can. You can write the initial state in this way. At this point, okay, Alice has to measure the two qubits in her possession. Okay, so it has to measure qubit A and qubit C. Okay, but has to measure it in the Bell basis. What is the Bell basis? The Bell basis is basically the when you have two qubits, again you have the canonical basis for the qubit that is, let me write it here. So we know that this is the canonical basis for one qubit. No, this is the canonical basis and the other basis for the for one qubit. So you have one qubit. When you have two qubits, you can have the canonical basis that is still 0, 0, 0, 1, 1, 0, 1, 1, or you can have something that is similar to this other basis here, which is exactly the basis where you consider the Bell states. Okay. Okay. So the qubit, you have this possible basis. Okay. It's the same thing that we had for one qubit. So what Alice does, measures qubit A and qubit C in the Bell basis. Okay. As you can see, so since here we have all the elements of the Bell basis, if she measures in the Bell basis, she will get one of these four possibilities, which means that the state will collapse into only one of these four terms. Okay, so the result of Alice's measurement is that the state of the three qubit collapses into one of the four states here, of the four terms, with equal probability. Okay, so after the measurement, the state of Alice and Bob together could be one of these four possibilities. Okay, so depending on the Alice measures if so depending on the outcome that Alice obtained, okay, Bob will have a particular state. So for example, if Alice measure phi plus, this means that Bob will have this kind of state. If she measure psi minus, then Bob is going to have this kind of state. So basically, Alice used 2 bits to encode the result of his measurement, okay? And this encoding is also known to Bob. okay? So if she get phi plus, the encoding is 0, 0, phi minus is 0, 1, phi plus is 1, 0, phi minus is 1, 1. Okay, this is standard encoding, okay, that everybody knows. So she uses her classical channel to send these 2 bits of information, classical information, to Bob. So, for example, if Alice measures this state here, she sent to Bob 0, 0, and Bob knows that his state is exactly the original state, the one labeled with letter C, that Alice wanted to send to him, right? Because the original state was alpha 0 plus beta 1. And he has in his possession exactly that state, okay? What happens if he receives 0, 1? He knows that his state is flipped. He has a phase flip. So in order to recover the original state, he knows that if he receives 0, 1, he has to apply a Z operator, and he has the original state. Same thing happens for the other 2 cases, okay? If he receives 0, 1, he knows that his state is the one with the bit flip error, let's say, so he recovers the original state by applying an X operator. Finally, if he receives 1, 1, he knows that his state is both bit flip and phase flipped, which means that he has to apply the operator zeta X in order to recover the initial state, okay? So in every case, so what happened is that Alice, so assuming that they pre-share an entangled pair, assuming that Alice and Bob pre-share an entangled pair, Alice can send the state of a qubit to Bob by communicating just 2 bits of classical information, okay? So some final comments, okay? First of all, quantum teleportation is does not happen instantaneously. Why? Because in order for Bob to reconstruct the initial state, Bob must receive at first the 2 bits associated with Alice's measurement. Until and so a classical, so he has to wait the classical information, which travels slower than the speed of light, no? So it's not instantaneous, to arrive to him, okay? So because he still doesn't know which operation to apply to his qubit until he has received the classical information, okay? And we know classical information cannot travel at the superluminal speed, okay? The second part is that quantum teleportation respects the no cloning. And that's because Alice, in order to teleport the state to Bob, had to perform a measurement, hence collapsing and so destroying her state. So we have this teleportation with let's say you only have teleportation when you collapse, when you destroy the initial state in Alice's possession. So you destroy means you measure it, okay? Some experimental realization of this protocol in 2020, some researchers, did some record, performed quantum teleportation using optical fibers on over 45 kilometers. And in 2017, it was implemented. This was the implementation via in free space, so ground to satellite quantum teleportation I think it was this this thing was done by some group that does quantum teleportation in China, and they were able to do it, so from ground to the satellite, over a distance ranging from 500 to more than 1,000 kilometers. Okay. So I think we can have a break, but are there questions concerning this part, or do you want me to clarify? Was it more or less clear, this part, how it's working, the protocol? Please write in the chat if you are still with me, if you have question, or if it's clear, or something. So yeah, the basic idea is that for those of you that never heard about this, is that you're not sending a qubit, you're sending the state of a qubit. That is a different thing. This is the thing that should think that must be clear. So okay, if there are no questions, let's see you in 15 minutes, more or less. So at 55. Okay. So see you in 15 minutes. Then we're gonna see super dense coding, which is basically the opposite of the inverse of teleportation, and then we talk about cryptography. Okay. Yeah, so see you in 15 minutes. Okay. Are you ready? You here? Many people connected? 40, more than 40. Okay. Okay, so let's start this second part. Do you have questions concerning the first part about the teleportation? If not, if you have, write in the chat. I'm gonna start the super dense coding part. Super dense coding is the following protocol. So Alice and Bob, they pre-share again a pair of entangled qubits, A and B. And Alice wants to communicate 2 bits of classical information to Bob by sending a single qubit. So they have a quantum communication channel that connects them. The idea is that by sending a qubit, she wants to communicate Bob a 2 bit of information. Okay. So the initial state is the one that we had before. So this quantum source is able to produce this kind of state here, 0, 0 plus 1, 1. So in super dense coding, okay, let's go on. Okay, so we have 2 bits again. One is A. So Alice has qubit A, B has qubit B. So what Alice does is to apply some local operation, some operation on her qubit in order to encode 2 bits of information. Okay, so like before, if she wants to encode 0, 0, she performs the identity operation, so she does nothing, doesn't do anything. So if she wants to encode the bits 0, 1, she performs an X operation to her qubit. If she wants to send 1, 1, she has to do zeta X operation. And if she wants to send 1, 0, it's the zeta. Okay. So you see that depending on the bit that she wants to send, she applies different operations that change the state accordingly. Okay, change the state in this way. Okay, so we start from 0, 0 plus 1, 1, but then, for example, if she wants to send 0, 1, the state become 0, 1 plus 1, 0. Okay, after the X operation on the first bit, that is the one. Sorry, Alice is the second bit here. Okay, so applying an X here that becomes 1, and an X here that becomes a 0. Okay, so you got this state here. Okay, then the first step is to share the 2 bits. Second step is to perform operation. Alice has to perform this kind of operation. And the third step is Alice used the quantum communication channel, to send Bob the qubit. So doesn't send the. So I mean, here you are sending the physical qubit. Okay, so it's not the state; it's exactly the physical qubit what you're sending in this communication channel. Okay, because it's a quantum communication channel. So she sent her qubit to Bob. At this point, Bob has to measure the 2 qubits in his possession in the Bell basis, okay? And depending on which basis, which outcome, outcome he gets, he will decode, he will understand what was the original message. So what was the 2-bit message that Alice wanted to send to him, okay? So in fact, if we measure state phi plus, so he can measure one of these 4, okay? So if he measure phi plus, he knows that the encoding was 0, 0. Again, if you measure psi plus, knows that the encoding was 0, 1, and so on, okay? So it's a super dense coding because sending just 1 qubit, you communicate 2 bits, okay? And somehow, so what's the difference, okay? In teleportation protocol can be thought like an inverted version of the super dense coding and vice versa, because somehow they swap their equipment, okay? So teleportation, so let me state this again. In teleportation, you transmit the state of 1 qubit using 2 classical bits. In super dense coding, you transmit 2 classical bits using 1 qubit, okay? Yeah, that's it. For what concerns super dense coding, I mean, the experiments I've shown, here the focus is more on the fidelity achieved by experiments, so which means the fidelity is the let's say the fidelity is the difference, let's say, the distance between the final quantum state that you obtain after the quantum channel and the initial state that you set, okay? So using optical fibers, in 2017, they reached the fidelity of 0.87. And in 2018, using particular photons, particular setup, Q quartz, they were able to reach a fidelity, so which means again the distance between initial and final state after the quantum communication channel of 0.998, okay? But using this particular setup, okay? Well, the first was about optical fibers, okay? So is it clear the difference between the two, or do you want me to state again? So in teleportation, you teleport the state of 1 qubit and you communicate 2 bits. Here you send the physical qubit and you transmit, so 2 classical bits, okay? Is it okay? Can I go on? Because now we have the quantum cryptography part that is similar, but maybe a little bit more challenging. Okay. So if there are no questions, I assume I can go on. Okay, something briefly about cryptography. Okay, you have so right now all the crypto systems. Yes, exactly. You need to in super dense coding. They pre-share these pair of entangled qubits. Yeah, this is the starting point. yeah, before anything happens, before you think about super dense coding, you have to pre-share these two qubits that are in entangled state, okay, before you do anything. But it's also true also for, yeah, exactly. Okay, so let's go on with quantum cryptography. Okay, so in classical, okay, cryptography. So when you have okay, there is another question. So how do you calculate the ratio of tokens? What do you mean, the ratio?
No, I'm sorry if this is really lame, but I'm not familiar with this area. So if you have to prepare your experiment before actually conducting it, that is communicating the one qubit from Alice to Bob, the prior communication supposes that you've passed information already, and that information consists in essentially entangling what Bob has, which is B, and what Alice has on her side. And so saying in the end that your densification of communication, or the dense communication, consists in communicating two classical bits with one qubit seems like off. But again, I'm sorry, it's just because I'm not familiar with this whole area of communication. Since you don't seem to count the prior communication to select the experiment.
Yeah, I understand that, but yeah, that's what you assume to have. Okay, so assuming that you have, so this is before the protocol. Okay, assume you have disentangled photon, and then you can perform the protocol. Okay, it's something this is not considered, and I don't think it can be seen as like some sort of communication that happens prior to the protocol, because you don't know the state of the, I mean, you basically do not know, so you do not measure the two states. I mean, the entangled qubit, okay? So you receive something, and yeah, I guess this is the idea. So you don't perform any. So before the protocol starts, you just receive this qubit, and you don't do anything with this. Yeah, and that's why I guess this could be considered like no communication. Yeah. You have to agree, yes. Or maybe, yeah, you just know, yeah, both of you have to know that this is the quantum state that I'm receiving is this one, okay? And then, so once you know it one time, then it works every time, okay? Yeah. So I can say, I know now, but then I can use, I know that the state is psi plus, then I can use from now on for the next 20 years, knowing that the state is psi plus, but you have to know in advance. But then I can use it, so as far as I know that the state is this one, I can use it infinite many times. And I can apply the protocol. So maybe that's the idea, okay? Yeah. So for example, Yeah, I know. So if I know, I want to send you 10 GB of that tomorrow, but I don't know. Yeah, basically, yeah, something like this, yeah. Yeah, that seems correct. Okay, so yeah, that's the idea. Okay, you have somehow to be in agreement about few things. So about the basically about the state prepared by the quantum source, but also you have to agree on the encoding. And once which could be standard, that it's a message that you do one time and then it works forever. Okay, that's the idea. Huh? Okay, so you have to to have already this information. Okay, however, let's go on. Okay, with cryptography. Okay, in what we usually use today is public key cryptography. So whenever you use, like in your browser and you check some website and there is the key symbol, it means that there is some RSA protocol going on. Okay, probably. So RSA is the technique that is widely used all over the world for public key cryptography. What does it mean? It means that I mean, there is a public key that is known to everybody and used by the sender to encrypt a secret message. Then there is a private key that is only known to the owner and only to the owner, which is used to decrypt the message. So the idea is this one. So you have some plain text, you encrypt using the public key, and then you the ciphertext, you send it, and the decryption is done via the private key that is only in possession of Bob. Okay. Okay, and then Bob is able to retrieve the original message. Okay, this is the idea of public key. So this is the RSA protocol. It's quite complex. So basically, so in order to in order for the crypto system to work, there are some steps that you have to follow. So you have to, for example, if Alice wants to send a Bob's to message, I mean, the idea is to share a private key, a public and a private key in such a way that only Alice and Bob know how to decrypt the message. So basically, Alice chooses a big prime number, and then chooses a number that is coprime with this other number here, that is p minus 1 times q minus 1, and then computes d such that d is e times d equal 1 q plus some number, some integer times this phi of n. So it looks like complex, okay? But maybe at the end, what happens is that for an eavesdropper to steal, okay, the message or the crypto, to steal the private key, what he has to do is he has to factorize this large n number n, okay? And we have seen yesterday that factorizing this number is hard, okay? So maybe here there is an easy example. So for example, if I choose P and Q to be 3 and 11, so my n, my large integer is 33, then I have to compute, so Alice has to compute this phi of n, that is p minus 1 times q minus 1, which is, of course, 20. So is 2 times 10 is 20. And then has to choose E, which is coprime with 20. Coprime means that coprime means that their common the common divisor is just 1. Okay, so for example, so which means that so if you take E equal to 7, this is coprime with 20. So if you take, for example, E equal to 10, 10 is not coprime with 20 because they both have 5 as a common divisor. Okay, so 7 is fine. And then you have to compute D times C modulus 20, which has to be 1. So you have to compute, I mean, you have to select D in such a way that this is true. So for example, if D equal 3 is okay because you have 3 times 7, and which is 21, which is modulus 20 give you 1. Okay, so if you select D equal to 3, it's okay. So the public key is going to be 7 and 33. So E is 7, N is 33. And the private key is going to be 3, 33. So D, which is this one. Yeah. Okay. So if you want to encrypt a 2, M equal 2, you have to compute this function here, which is 2 to the 7 modulus 33, which is 29. And then in order to decrypt, you have to perform C to the power of D modulus 33, which is 2. So okay, it's a bit complicated, but at the end, yeah, you can share this private key. Okay, and the only way an eavesdropper can steal your message is if this eavesdropper is able to factorize the number n. Okay, so okay, we know. Okay, in theory, it is possible to establish the private key, but you have to solve this problem. This is very hard for classical machines, which is integer factorization, and we know that the runtime of the best classical algorithm for factorization is scales exponentially with the size of n. Okay, so which means that I think here the largest number ever factorized has 230 digits, and it takes a lot of operations. Okay, 9 to the 10 to the 24 operation. Okay, so we've seen the other day, that in order to factor a number of dimension 2048, that is the one implemented usually by RSA, you will need to run this algorithm, which is the best classical algorithm, on a classical computer for billions of years. Okay, and that's where, so Shor algorithm, as we've seen the other day, gives you an exponential speed up with respect to the classical algorithm. So you can factor the same number in a matter of seconds if you have a powerful enough quantum computer. Okay, because it's no more exponential in the dimension is only polynomial. Okay, so you go from millions of years to a matter of seconds, let's say, or minutes, to factor a 2048 digit number. Okay, but so let's say that quantum mechanics with the Shor algorithm creates the problem. So if you have, which means that if you have a quantum computer, you can crack you can break the RSA cryptography, okay, with the Shor algorithm. But so it's a problem because, yeah, of course, everything. So all the security that we use today is based on RSA, and so it's a problem if somebody has a quantum computer able to run Shor algorithm on large numbers. Okay. Now, quantum mechanics also provide the solution to the problem that is created with the Shor algorithm, and the solution is quantum cryptography. And with quantum key distribution, that is a way of communicating in a secure way. What's interesting about quantum key distribution? So again, it's a system for assuring secure communication, which enables two parties, which are Alice and Bob, to produce and share a secret key, only known to them, which they can use to encrypt and decrypt their messages. Okay. And the best thing about quantum key distribution is that relies on the postulates of quantum mechanics, or the same that we have seen for quantum computation. Okay, relies on the postulate of quantum mechanics, which means that security is guaranteed by the laws of nature. Okay, of nature. So it's quantum mechanics itself that protects your information somehow. Okay. And this is fundamentally different compared with traditional classical methods that are based on the computational hardness of factoring, for example. Okay. So not only so the security is guaranteed by the laws of physics, not something that computationally hard, but the second feature is that, in contrast to what happens in classical protocols, quantum key distribution can also provide indication about possible eavesdropping. So if someone, if someone is trying to spy on Alice and Bob, so Eve, this third part Eve, is trying to obtain information, trying to spy on them, so obtain information about their secret key, from the principle of quantum mechanics, quantum physics, involving the collapsing of this wave function associated to the quantum state after the measurement, Eve, every time if Eve tries to obtain information, she will measure somehow the quantum state and then disturb the communication, okay? The quantum system that perform the communication, okay? So this means that Alice and Bob, if they notice something strange, they can detect the presence of a third party Eve that whose presence disturb the quantum state because of the principles of the postulate of quantum mechanics. Okay, because measurement disturb the state. So what's the setting for quantum key distribution? So we have Alice and Bob that wants to share this random key, secret key, and they have both a quantum channel and a classical channel, so they can communicate both via quantum channel and the classical channel. And Eve is trying to trying to obtain information by looking at these channels. Okay. Okay. Especially the quantum channel, because everything that Alice and Bob So everything that goes inside the classical channel is going to be public. Okay, so if Eve wants to tries to spy on them, has to act on the quantum channel. Okay, then let's start. Okay, quantum key distribution involves different steps. So the first one is the following. Okay, so Alice uses 2 random bits, A and B, in order to prepare a qubit state. So a single qubit, you know. AB is these are 2 bits that allow you to prepare one of the 4 possibilities. Okay. So Alice basically tosses a coin. If she gets two heads, prepare the state 0. If she gets 2 tails, she prepare the state minus. 1 head, 1 tail, 1. 1 tail, 1 head, plus. Okay. So in other words, the second bit. So if the second bit is 0, it means the canonical basis. If the second bit is 1, it means the plus or minus basis. And the first bit tells you 0, 1, or plus or minus. Okay. So yeah, that's the first encoding. So and this is a single qubit. These are single qubit state. Okay. So Alice send the qubit via the quantum channel to Bob. Okay, so Bob received the state received this qubit whose state is psi AB. Okay. At this point, so we have the third step where Bob throws a random bit, so like Alice did, but now Bob tosses a coin, and depending on the outcome of this coin, of this random bit, it decides how to measure the state psi AB. So for example, if the random bit B prime has value 0, then it will measure in the Z basis, which means Z basis is the basis where 0 and 1 is the basis of measuring along Z means measuring along 0 along the canonical basis. And if the random bit has value 1, it means that we will measure along X, which means we will measure plus or minus. Okay. Then once he measured his qubit, Bob saved the result of the measurement in a bit. So he will save 0 if the outcome is +1, -1 if the outcome is -1. So here, as you can see, okay. So if he decide to measure Z, so if he measure along Z, if you get the plus here as a eigenvalue, it encodes into a bit 0. If it gets a minus, it encodes it in the state 1. Same thing if he measure along X. Okay, so this is clear. Is it clear so far? Please write in the chat. Write okay in the chat if it is clear. Okay. So basically, Alice and Bob repeat step 1, 2, 3, and 4, a number of times equal to n. And then Alice and Bob publicly share their strings, B and B prime. So B, what is B? B is the second bit, the one associated to canonical basis or plus minus basis. So B is this bit here. And B prime is the random choice about the measurement, okay, along Z or along X. So, and they publicly share the string B and B prime. They also discard all bits belonging to these two strings B and B prime. So they discard all bits of the two strings except those for which B prime, so the single bit B prime, is equal to B. What does it mean? It means that whenever B prime is equal to B, it means that Alice prepare a state in the basis X or Z or X basis, and Bob measured in the correct basis. Okay. So in this way, they discard all bits except those for which B prime equal to B. Okay. This means that the bits that they obtain, so the bits in the string A and A prime, the two strings A and A prime, will be equal when for those bits that have B prime equal to B. Okay, because they measure. So the first step, so this step here tells them that we perform that Bob and Alice prepare the state and measure it in the same basis, and by consequence, alpha prime and A prime and A will be the same. Okay. The remaining bits, so asymptotically n over 2, because half of the time Bob gets the right basis, half of the time not, on average. So the bits will satisfy, so the relation A prime equal A. And then those bits that satisfy this relation constitute their secret key. This maybe is more intricate. So let's see an example. Okay. So these are all the possible cases. Okay. Let's say Alice. So B for Alice is let's say B for Alice is 0, which means the basis she prepare the state is Z, which means that she encodes 0 into the 0 state. Then she sends the qubit to Bob, and Bob has these two choices. Bob throws a random bit B prime that could be 0, 1. So if so, it's going to be half of the times, so 0 half of the times 1. So if by chance he gets 0, he will have choose to measure along Z, which is the same basis that Alice used. Okay, this means that the result of Bob will be 0, which is the same that Alice encoded. Hence the probability, I mean, he will get 0 with probability 1, so for certain, because the state was 0 state. Okay, and so A prime will be 0. Okay, which is in accordance with what with the A that Alice had. Okay, let's say instead that Bob by chance measure in the X basis, which is not the correct basis. So B prime is not equal to B. In this case, Bob has two possibilities. So since the state is 0, but he measures X, Bob is measuring plus or minus. So he will get 0 half of the times and 1 half of the times. So here, what he gets is 0, which is correct. It's the same result that we have in the previous case here, but they have to discard it because B prime is not equal to B. Okay, that's why they discard it, because it was not coming from a correct measurement. Okay, it was just a possibility. Okay, happened by chance to have the same value. Okay, so basically, again, so the meaning is that they perform this multiple times, and they consider, I mean, the A prime will be equal to A only when they select B, only when Bob measuring a base is B prime, that is the same as the one used by Alice, B. Okay, that's the meaning. So you have 4 possibilities. Okay, for example, when if Alice prepares state X and encodes 1 into the minus, which means that has to encode 1 into the minus, and then send it to Bob. If Bob measures Z, you're not measuring the same basis, which means that the outcome for Bob will be random in these two when he measures Z. Instead, if Bob measures X, he will get the same state that Alice prepared, and with probability 1, okay, with eigenvalue -1, which he encodes into the bit A prime. Okay, so that's why this is correct. Yeah, it's okay. Before going on, is it okay, this part, or do you want me to explain again? Maybe so. It's not probably immediate to grasp, because yeah. So basically, they are yeah. They check the strings B and B prime in order, and check them bitwise in order to understand if the strings A prime, so in order to understand where, in which bit, the strings A and A prime coincide. Okay, on average, it's going to be half of the string, half of the bits are going to be in are going to be the same, half is going to be different. Okay, and they only take those that are the same. Okay. If there are, yeah. I think so. Are there some questions concerning this part? If there are no questions, or please write in the chat, or use your microphone. Okay, because now things get even a little bit more complicated, because we now consider the case where we also have Eve that is trying to spy on them. Okay, so let's imagine that Eve wants to intercept the secret key, and the strategy that she used is an intercept reset, which means that she intercepts the qubit sent by Alice, measure it, and then send back to Bob the state she measured. Okay, so let's see what could happen. So here we restrict to the case where Alice chooses the Z basis and send a 0 state. Okay, so basically this first part. Okay, this first part. Okay, here. Okay, basically, okay, in briefly, okay, if Eve uses in the measurement the same basis that Alice used, then can perfectly understand the bit encoded by Alice. And then, which will be the same bit measured by Bob, okay? So in that particular case, Bob and Alice cannot understand that Eve was in the middle, okay? Because Eve measure in the correct basis. But instead, if Eve measure in a different basis, then her bit, the bit obtained by Eve will be random, and so by consequence also the bit measured by Bob will be random. Okay, so let's see this in the table. Okay, when Alice prepares the state 0, so the basis is Z, and Eve measure in Z. Okay, she gets 0 with probability 1, of course, because the state is in 0. Then she sends the same state to Bob, which measure again in Z. And okay, and here in this case, Bob and Alice cannot say anything. Okay, the presence of Eve didn't change the state at all. Okay, but in all the other cases, Eve did the wrong choice in the measurement. So measure X instead of measuring Z. So this means that she gets a random answer. So she gets either plus or minus. She sends the same answer to Bob, which measures instead in the correct basis. So he measures Z, but gets in this in the last 4 cases something that is random. Okay. So basically, here, in this case here, oh sorry, in the 3rd case and in the 5th case, you get the wrong result. Okay. Okay, again, so if Eve uses a different basis from the one used by Alice, then its bit will be random as well as the bit measured by Bob. We already said that. So when Eve uses a different basis, she destroys the state originally prepared by Alice. So how can Alice and Bob understand if Eve is in the middle? So basically, Alice and Bob can extract a part of their secret key and make it public. Okay, so they do not share the full private key, just a part of it. Okay, so they make it public a portion of their private key. Since this is what happens, so we've seen this before. So in this case, Alice preparing Z and Bob measure the correct solution. Okay. By checking their private key, if they notice that asymptotically 1/4, so 1/8 plus 1/8 is 1/4 of the times their secret key are different, even though they measure the same basis. So even though Bob measured the same basis that Alice prepared, they can claim that there is an eavesdropper in between them. Okay, because otherwise they would have the same result, A and A prime. Okay, but if is in there, they expect 1/4 of the time to have errors in their secret key. Okay, that's how they can claim that there is something that is spying on them. Okay, is it clear, this part? Okay, so Eve just measure randomly. Okay. Are there any other questions concerning this part? What do you mean? What's the difference between what Eve? So Eve is measuring the qubit. What's in the man in the middle attack? So it's not what Eve is doing.
I mean, what Eve is doing here is basically trying to eavesdrop. If instead she goes in the middle of the connection and pretends to Alice that she's Bob and does all the communication with her that Bob would have done, including the cross-check of the public part of the key, and then turns around to Bob and does the same, pretending to be Alice, that's still not something we could detect unless Alice and Bob at some future date start communicating again and notice that they have different keys, actually.
So, but at some point, so Bob or Alice, in this case, I guess, so Bob will notice that he received 2 messages or not?
Well, no, the idea would be that you would sort of cap the connection. Bob never gets Alice's message.
Okay. I don't know. I don't know if this, because, okay. In this case, it means that, okay, since the classical, the quantum channel, okay, Eve has to be in the middle, so has to intercept, okay. But for what concerns the classical channel in quantum key distribution, everything is public. So, so my idea is it's hard to pretend to be Alice or Bob if you're doing the classical communication part. If your classical communication is public, so I can post, I don't know, on Facebook, I don't know, my string.
Yeah, I see. That makes sense. Yes.
So I think at some, so it's hard, at least for Eve, to completely obscure the classical communication of Alice to Bob or vice versa, because it's always public, the classical part. So I guess there could be something like what you say, but then Bob has to like notice at some point that there are 2 Alices that are telling different things. Okay, this is my idea. Okay, but yeah, probably there are more, again, more complex strategies that so, but then start to be more intricate. The thing that instead of intercept and resend, that Eve can do, but still with some probability. There is some probability of error for the public key. Okay, but so maybe what I know is that intercept resend is not the only strategy that Eve can have. There are other that could be more complicated that may lower the probability of error. So maybe lower than 1/4. But yeah, I'm not even an expert of that part. So this is what is usually considered, okay, as the standard setting. So, so what about experiments? So we have QKD 2015, 2017 over optical fibers, over ground and aircraft. And okay, this was the science at University of Science and Technology of China performed the QKD at space scale. Okay, maybe it was this one from China. And there are also many quantum key distribution systems in the market. And there is, for example, ID Quantique. If you Google them, so it's like a company that sells their quantum key distribution systems, and yeah, there are other ones all over the world, and also these are centers that have a quantum key distribution network, so which means that their privacy is ensured by this quantum key distribution protocol, okay, inside their network. So these are those that have, I mean, a physical implementation of a QKD network, okay, inside their laboratories, let's say. Okay, I think, okay, there is one more thing. So we already seen this part. So quantum creates the problem with the Shor algorithm, but also the solution with the QKD for the secure communication. But then, okay, another way, which is a classical way of overcoming Shor algorithm, is to use something is called post-quantum cryptography, which means a classical cryptography, but that is based on different approaches. So symmetric cryptographic algorithms. So basically use hash functions, or problems that are not factorization, that are considered to be safe from the attack of a quantum computer. Okay, or at least we still for which it is not known if there is a quantum algorithm that can solve this kind of problems. Okay, and probably it doesn't exist. No, it can do it in polynomial time. Okay, so these are some cryptography, and there is this. So the NIST, which is the National Institute of Standard and Technology, I think, from US, that already has done this call for standardization. So the idea is, okay, quantum is coming, so we have to be ready for post-quantum cryptography, which means classical cryptography that is protected by the attacks of quantum computers. Okay, so that is gonna replace RSA in the next 10, 20 years, maybe. Okay. Okay then. I think that's it for today. Do you have any question concerning this part? So write in the chat or speak. How many of you are still here? Or so write something. Everything is you. If you are still here and more or less awake, or otherwise, yeah, don't say anything. Still alive? Yeah, some of you are still alive. Okay, we have to reach at least 25% of the people, I hope. 1, 2, 3, 4, 5, 6, 7 people. How many of us?
8.
8. Okay. So there are 50 people. We need 2 more. 2 more that are not. Okay, probably, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 11. Okay, probably. Yeah. Okay. We reached the threshold of 20%. So, okay. Again, if you have question, please. Yeah. Okay. Far beyond the 20%. Okay. So, do you have any question concerning this part? So, if not, okay, let me say tomorrow there's gonna be the lecture by Lorenzo Roccuto and Marco Maronese. Marco in the morning, and we will talk about quantum. Let's see. We'll talk about, so we'll have a brief introduction about classical concept in machine learning, neural network, and then you're gonna see how perform quantum machine learning on basically gate model quantum computation, and then and it will cover some of the things that we have seen today very briefly with quantum variational classifiers and quantum supervector machine. In the afternoon, there's going to be some advanced use of quantum annealing for again, quantum machine learning. In particular, quantum annealer they are good for training something that is called restricted Boltzmann machines, that are particular kind of neural networks. And then at the end, I'm gonna present you our last work that we did in collaboration with D-Wave and the University of Polytechnic of Milan about molecular unfolding using the quantum annealing. Okay, so yeah, that's it. So if there's nothing that you want to say, thank you for your attention. Don't know if Daniele want to say something. Okay.
Yes, no. Just to say hello. So thanks, Riccardo, for this lesson, and I wait you for tomorrow for our last lesson. Time is very it's flight, and yes, thank you a lot, everybody. See you tomorrow.
Bye. Thank you.
Bye.
Ciao.
Bye.